Okay, maybe we're ready now. Hopefully everyone can hear me. Okay, so welcome back. Still a few technical issues. Hopefully we'll get around this. We are back at machine learning. Oh wow. Okay. CIS 519. So let me just start by reminding you where we are. This is our second meeting. You see that I added my background to remind ourselves that we are in Philadelphia. This is the Rodin Museum. Hopefully many of you have been there. And that it's about thinking. This guy is going to help me remind you that. So what is it about? So this is just a brief course overview. We discussed this last time. We're going to talk about it a lot as we go. We're going to start today with some introduction to basic problems and questions. And hopefully we'll also start with the detailed examples that will give us some of the key algorithmic ideas we'll see later in the semester. We're going to talk about basic paradigms of machine learning, discriminative learning and generative learning, talk about learning protocols, and cover throughout a range of algorithms. Each one of them is interesting in its own right, and we'll see also relations between them. Talk about modeling, evaluation, various challenges. So please mute yourself if you're not. Okay. Could you please mute? Okay. Okay, maybe better now. So okay, so this is to remind ourselves that the class is recorded, and it is recorded now. And the recording is going to be available on the website. Okay, so just again, some administration. Everything is the same as what I said last time. We already started with office hours, both mine and the TAs. We're going to announce locations. Everything is also going to be on the website. Please come. I want to remind you that homework 0 is outside. This is really a good yardstick for you to figure out where you are on the math preparations for the class. Registration is all done. I think all the people that wanted to be in the class and did not have conflicts are in the class. If you think that that's wrong, let me know. And basically go to our website, go to Piazza, everything, all the communication is going to be through there. Okay, so I talked about homework 0. And I really want to make this class interactive, not the easy way to do it, given that we are all online, but we're going to try. I'm going to ask you a lot of questions. We're going to try maybe to use the raising hands that you can also use, and maybe open the mic from time to time to allow you to discuss it. One reminder about the structure of the class. So the class is called Applied Machine Learning. In the class, we're going to mostly see machine learning, trying to understand the basic principles, the key ideas, the key concepts, the key algorithms. The applied is going to be mostly in the homework. You're going to apply it. Each homework is going to be like a small project. So don't be surprised that you see that the homework actually complement what we do in class. They don't just mirror it. You're going to learn things in the homework just because there's a lot of stuff introduce in this topic. Okay, so we sent you a survey. Many of you responded, so thank you. And I just want to highlight a couple of things that were prominent in the survey. One is math background. Most of you think that you do have the math background. Around 10%, 10 to 15%, depending on the topic, think that they don't. Again, homework 0 is your yardstick. If you feel bad about homework 0, you cannot do it. You know, after spending a few hours, it means that you haven't seen the concepts. And my suggestion would be to basically take the math classes required and then come to the class. We are going to add a recitation next week that will help with that. But still, your own decision on whether your math is mature enough for the class or not. Computation. We are going to provide some guidelines of when the homeworks are out on how to compute, what resources to use, and so on. Time zones. So several of you are concerned about time zones. Actually, it's not that bad. I was concerned that it's going to be worse. So here is the distribution that we have. The vast majority of you, well, the vast majority is here on the East Coast. All but 3 are in what I would count as reasonable, between -3, which is California, West Coast, and +12, which is China. Not ideal, but still doable. And 3 of you are in time zones that I would consider unreasonable. You can still join if you want, but we wouldn't count it against you. So we will definitely take this into account when we look at attendance and participation. So if you have any issues with this, drop me an email, let me know. Some of you were concerned about additional time on exams. So Penn has standard ways to deal with it. If you don't know how to deal with it, let me know and I'll give you some pointers. I don't know that it's going to be an issue this year because everything is going to be take-home exams and you'll have enough time, but still, if you're concerned about it, let me know. Okay, so just a few more words about policies. I talked about it last time, and this is the last time I'm going to talk about it. Cheating. The policy is no, and I really hope that you'll take it seriously because we take it very seriously. There are policies of Penn, and we're going to look at it and, as I said, take it seriously. However, this is not a mandatory class. So my assumption here is that you are all adults and you want to be here because you want to study machine learning. So you're going to take this seriously, you're going to make an effort, and I'm counting on that. Other policies. Homework. As we said, collaboration is encouraged, but you have to write your own solution and code. So that's really important. This is where learning is being done. We have a late policy, credit of 4 days. That's it. I think it's sufficient. Just monitor it and don't use everything at the beginning. This is our current policy for grading. Things are going to change a little bit here and there because of we'll make a final decision on how to take participation into account, but it's going to be about 5%. And that's basically it. Here is one other question that you probably want to have the answer to, grades. So this is a histogram of grades from the last couple of years. This is the distribution that we have. So about 40% is A's of some sort, A plus, A minus, about 40% is B's, 20% is C's, and very few will get below C. Basically up to you. I mean, so everyone who's going to make the effort in the class, do the work, is going to get good grades. So that's it. Just a few more pointers. Not all of you are on Piazza when I last checked, so make sure that you are there because a lot of information is going to go through that. Okay, so let me open the floor to this. It's not easy for me to follow the chat during class. So the TAs are going to alert me if there is something really, really important, but I'm going to count on you to respond to my poll everywhere questions and interact this way, much easier for me. So I'm going to take a few seconds and see if we have any important questions. Okay, so okay, that's a simple response. No questions. No, the whole grade is not 120. There is a formula on the website that explains how we include the 20% of the project. So go to the website and check it. The grades are curved. So basically, this is going to be very close to the distribution. Once you have 150 students, we know what the distribution is. I mean, if the test is a little bit too difficult or a little bit too easy, doesn't really matter. So let's see. How the late works. Let me just look this. The late policy, basically, we monitor and you monitor how late you are for each problem set. Once you exceed the 4 days, we don't accept homework from you. So it's actually very simple. The system records when you submit, and we know when the deadline is, so it's easy to do. Where are the slides posted? The slides are posted on the website. Already you can see their slides from last year. They're all there. And following each lecture, I'm going to post the slides of today's lecture, just because sometimes I make additional changes as a function of questions that you ask in the class. We're going to talk about projects later. If you have questions about your email and whether your response is recorded, ask the TAs. I think the answer is yes. Hopefully we don't have any technical problems. Yes, attendance is being tracked via this participation. So don't be logged in another account, just log in through your PEN email. Okay, so let's, okay, so issue of undergraduate grant section grading. I always look at the distribution of undergrads and graduates to see if they are significantly different and whether there is a need to do something separately. In the last few years, I haven't seen the need to do this, but don't be concerned about it. Okay, so let's stop with this. Thank you, and let's move on, if PowerPoint allows me. Okay, so my goal today is really to introduce some of the key concepts in machine learning at a high level. We're going to talk about representations. We're going to talk about the supervised learning protocol, and we're going to introduce a few new concepts like instance space, label space, a model, and a hypothesis space. So let's start, and we're going to start with the badges game. So let me remind you, you all saw it. Hopefully you all thought about it. Hopefully you can see this. Can you?
Yes.
You can. Okay, excellent, thanks. So this is actually a real story. This was my first or second conference quite a few years ago when I was a PhD student. And the program chair of the conference decided to play this game. When you register to the conference, you got your badge, and on the badge, you had a plus or a minus. And the question was, what's behind it? What is the unknown function that was used to generate the plus or minus? So this was a puzzle to the machine learning conference attendees, and this is your puzzle too. And it's really an interesting machine learning question just because it brings up a lot of interesting issues that I'd like to discuss now. So, okay, let's see what's going on here. Okay. So of course, this is a supervised learning problem because we gave you data and we gave you a label, positive example or negative example. And this is the key protocol that we're going to study this semester. And I'm still, for some reason, fighting with this presentation. Not sure what's happening. Okay, let me exit the presentation and see why this is misbehaving. Okay, so assuming that all of you thought enough about this badges game, I want to ask you some questions about it. And these questions are going to bring up some question that I'd like to discuss. So let's first, I want to know whether you know the answer and whether you're confident about it. Now, don't tell me the answer. We're going to get to it later. I just want to know what do you think? Okay, so I see a lot of C's here, but not D's, which means people thought about it and didn't get it. That's my interpretation. Change your answer if my interpretation is wrong. Okay, but I see that close to 10% are really sure. Not only that they know it, but they're really sure that they know it. Okay, so let's move on. If you know the answer, and I'm not gonna show the responses now, tell me why. Why are you so sure that you have the right answer? Don't give me the answer again. Just give a concise explanation of why you think this is the right one. Now, this is actually an interesting question, and you will see later why, because as we will see, machine learning provides eventually models, functions that we're after, but it's not a deterministic process. Nevertheless, some of you actually are very sure that you got the right answer. So I want to know why, and this answer is going to give us some insight into important issues in machine learning that eventually we'll be able to quantify. So let's see. Okay. So I didn't get a lot of responses here. But some of you said that you are very sure that this is the right answer. No argument for why?
I submitted one, but it just hasn't shown up.
Oh, what did you say then? Thanks for letting us know.
Well, I said that it held true for every instance, and it was very straightforward to check that it held true. But it doesn't mean that it's the right one. It could be a coincidence.
Okay, so first, thanks a lot. So the first part of your answer is it held true for all the instances. And I assume all of you that got the answers verify that. But let's see, is this sufficient? Because you say no, why isn't it sufficient?
Well, it could be a coincidence, right?
It could be a coincidence, and moreover, it's very easy to be consistent. I can just I can print it on a piece of paper and show it to you. This is my function, and this function is consistent with all the data, right? So being consistent with all the data is relatively easy. I can just remember the data. So really, you have a better reason that it's not easy to articulate. Any other suggestion for why you're sure? I actually think that you have a better reason, but it's not easy to say it. Yes, Stephen.
I answered, I said that the probability that it's false is close to 0.
How do you know that?
Just by modeling it on the data or looking at the data set and comparing a hypothesis to what the data set shows.
I didn't get that.
I said by reviewing the data, making a hypothesis and see how closely the hypothesis relates to the data set.
What does it mean relates to the data set?
Well, if we have the right answer, then it'll be close to what's correct.
So maybe what you want to say is something like, I looked at some of the data and used that in order to come up with my function, and then looked at some other part of the data that was not used to come up with the function, and it worked on that too.
Yes, yeah.
Okay, so that's a slightly better protocol because you kind of trained your model, let's call it, on some of the data and then tested it on another part of the data that was not observed during the training. And you got it right. Okay. So all of you are saying about the same thing. Either they're not sure or some form of consistency with the data. I'm going to suggest one other thing. And that is your function. I suggested that the solution just print it on a piece of paper and show me the mapping. There were 200 some examples there. So this is a very long function. How long is your function in characters? If you have to write down the function, don't write it, but just let me know. I bet it's probably very, very short. And I think that's part of your conviction that it's true. It's a very simple solution. Maybe it means that it must be true. So let's keep this in mind when we talk about it. The simplicity of the solution is actually one of the reasons you're so convinced when you got it. Now, a few other questions that I want to bring up, but I want to just remind ourselves, this is the data. There's a lot of data there, you know, for normal human beings, a lot of examples, and this is how it looks, right? So some pluses, some minuses, and you can also think about it as having some test data that you haven't looked at the pluses and the minuses, and you want to know, so Shivani, who is now a professor here, is she a positive example or a negative example? She wasn't in that conference. Okay, so we have two versions of the problem. We have the version that was presented to the conference attendees. And we have the question that I asked you, and all of you seem to agree that ours is easier. Oh, not all of you. Some of you think that it's theirs. Okay, what's this? So, okay, vast majority still think that it's ours. So let's see why. Here's another question. Say ours or theirs, colon, why? So that's not an easy question, but all of you have some intuitions about it. Okay, so ours because we have access to full data. That's one good reason. The conference attendees had to go to look at people and pick at their badges and understand. Okay, because they went to the conference focused on machine learning and we've barely started the class yet. That means that theirs was easier. But let's see, so what were the options that they had when they looked at the badges? They saw someone that came from Australia and he was a plus, and someone that was 6'3", that was a minus, and someone that had shoe sizes, 13 and was a plus. So they had a lot of options of what this plus or minus depend on. On the other hand, what are your options for what the plus or minus depends on? It's only the name. I kind of gave you a partial answer by presenting it on a piece of paper and telling you it depends on the name. It's not the height, it's not where you're from, it's not your shoe size, it's not anything else. It's really the name. In this sense, I focused you quite a bit, and I think your problem is much, much easier. Any comments or disagreement with that? Next question on this. That's an even harder question. So our goal eventually is to write programs that take as input this data that I gave you and produce what some of you have in mind, which is a function or potentially a prediction. Okay, use machine learning is good. Maybe you can be more specific. Okay, so all of you are really giving good answers. So find a regression between plus, minus, and name, which is good. But then someone suggests likely related by characters in the name needs some way to check similarity, which is good, which means, okay, some of you have some clues about the answer. I can see that. There are probably better ways of saying it. Cleaning and sorting the data. The data is relatively clean, although we will clean it a little bit more when we present it to you. Okay, so a lot of the solutions that I was hoping to get from you is things like, okay, I see linear regression. I was expecting to see use neural networks because you read the newspapers and you know the neural networks are hot. Google, I don't know how Google is going to help us. But let's see. So here is a more detailed example, a question. How do you represent the input? So I gave you the input just as strings. That's probably not going to be good enough if you want to write a program. How would you represent it? In numbers, array of characters, 2 arrays. Okay, vector is good, but the vector is too abstract for us because we don't know vector of what. Okay, data set of features from names, number of characters, vowels, each letter, sequence, names goes to 1 and 0, and so on. Okay, length, numbers. Okay, excellent. So hopefully most of you had to spend a little bit of time, at least here, if you haven't spent time earlier, to think about it. So we also spent a little bit of time thinking about it. And I'm going to present some experiments. But before that, I want to ask you for the truth. Some of you that know it. Okay, second letter of the first name was a vowel. And that makes it a positive example. Agreed? Check it, look at the data. That's the right answer. Very simple function. And that's why convincing. So since this is a machine learning class, what we try to do is to try to run neural network on it. So here is the first model. The input is, say, my name. We tokenized it. So we just take 2 tokens, first name, last name, and we use it as a representation of the input of a neural network. MLP stands for multi-layer perceptron. All the parameters are here. It really doesn't matter so much. We split the data into training, 234 examples, and to test 60 test examples. And we basically had a vocabulary that consisted of all the words in the data set, both training and test. And the representation that we use is something that we're going to call one hat, which basically means the number of features I have is the number of words in the vocabulary. And then is one of them. So then is encoded as, then is the fourth word in this vocabulary. So it's encoded as 0001 and the rest zeros. Worth apparently is the second. And it's encoded as 01, the rest zeros, and so on. This is being fed into a neural network, and that's the results that we get. So of course, the training accuracy is 100%. It's very easy to basically memorize the training data. But the test accuracy is only 58%, which is quite disappointing. Anyone wants to suggest what we should do next? So the model is not good enough. So instead of just using this relatively simple feed-forward neural network that we're gonna, of course, talk a little bit more in the class, or a lot more about how to do the learning here and a lot more things, we actually move to a very, very expressive model, one of the hottest model today in the market. It's called the T5 model. It has 3 billion parameters. 3 billion is a large number, more than the number of names that we have in the world. Again, training accuracy is 100%, but test accuracy is even worse. It's only 52%. So what's happening here? Why can't we learn this?
There's no real relation between the data and the outcomes.
What do you mean?
That you can't guess the result based off of the input name. Like it just doesn't correlate well.
Exactly. So the representation we chose is not good. It's not, the function does not depend on the names, or not at least on the tokens. So it doesn't matter how powerful the model that we use, it's not going to learn it well. It's not going to generalize. We used this word last time. So I need to change not the model, not the algorithm, but rather the representation. So let's move to a character-based model. I'm using the same neural network as before, feed-forward neural network. This time, the representation is of characters. So my input is going to be characters. All I have is these characters that you see here on the right, A, B, C, D, E, up to Z. And I have two words. So the left here represents the first name. The right represents the second, and so on. And I'm going to represent all the characters of the first and the second and the last name. And I'm going to feed this to my neural network. Hopefully, this is a better representation. So again, A is represented as a vector of where 1 and the rest zeros. B is going to be 0, 1, and the rest zeros, and so on. Now, when I use a character-based MLP, again, training accuracy is 100% as expected. I'm getting 92%. Still a little bit disappointing because you guys that guessed it got 100%. And it's a very, very simple notion. So why is that? Let's try something else. Let's try a character-based model with only the second character as input. It got it, not surprisingly. So the lesson is that, or at least one of the lessons is, the model is not that important here. What really important is the representation. And even with a pretty good representation, the third row here, the character-based MLP, we didn't get it completely right as expected. So that shows us, or first lesson in showing us, the importance of representation. Really, really crucial. And this is why I thought that the problem that you had is much, much easier than the problem that the conference attendees had, because you already knew that it depends on the characters, or the words at least. You didn't have to deal with shoe size and height. So the set of representations you have to consider is much smaller. Now notice that the right solution that you gave me depended on the notion of a vowel. The second character is a vowel, but vowel was not part of the input. So really, if instead of a vowel, the second character would be X, Z, B, D, or K, I think you will be less convinced that this is true. Think about it. Let's just replace the concept with, instead of second character being a vowel makes it positive, second character being one of Z, X, K, B, D makes it positive. I think all of you will be less convinced that this is the right solution. And this is what happened to our neural network. It did not have the notion of a vowel, so it had to list them. And maybe one of these vowels didn't appear a lot in the training, and it definitely didn't get it. So this background knowledge that you had helped you here, not only in learning it, because you immediately identified that vowels are important here, but also in being convinced that this is important. Okay, and then the question is algorithm. How do we write a program eventually that takes this data and predicts the label? And this is something we're going to get to later on. Okay, so really, the way I want to think about machine learning as opposed to traditional programming is this. So in traditional programming, you start with some data, you come up with the rules with the program, and as you run it through your program, you come up with some answers. On the other hand, in machine learning, we have the data and the answers, which are the labels. And then we hope that once it goes into the machine learning program, it comes up with the rules. In this case, the second character should be a vowel for this to be positive. Or with some program or with some other function that we can eventually evaluate on the data. So that's kind of the different paradigm. Now, in some cases, this is really important. Think about this example. Think about, rock, scissors, paper. This is a very, very good example where traditional program isn't going to work, right? If you want to look at these images, identify, is it a rock or a scissor or a paper, it's going to be very difficult for you to write this program. Similarly, in the example of the spelling that I gave you last time, if you want to correct this, trying to write a set of rules is going to be very difficult. Or the categorization example, take my email and file it into different folders. Again, writing a program is going to be very difficult. But in some cases, maybe it actually makes sense to use traditional programming. Machine learning isn't going to be the solution for everything. So if I ask you to sort these numbers in decreasing order and you want to write a program for that, probably makes sense to think a little bit about it and write a program rather than using a machine learning procedure for this. This is something that you should think about, because maybe you do want to use machine learning in order to do sorting. Question, comments before we move on? No questions. So hopefully you're convinced that for sorting, you don't use machine learning. You don't want to use machine learning. Maybe some of you would like to use it for sorting too. I'm not sure. I see that a lot of you responded, but okay, it's just coming up now. Okay, so
Sorry,
no
I
question.
did have a quick question that I guess it didn't show up yet.
Yeah, go ahead.
Sure. So I was wondering, on the previous slide, you had a diagram that says for machine learning, we put answers and data in to like some algorithm and then get rules out. So I was wondering how this works with sort of black box neural networks where we can't exactly explain how the network made a decision.
So your question is, really the output is not rules. The output is some way to compute a function, but I don't really understand what it computes.
Right.
Yeah, so that's a very good question. So rather than rules, what I'm going to have here is a model that knows how to compute predictions, compute answers on future, previously unseen data, but I wouldn't call it rules, you're saying. And that's actually a very, very good observation, and we're going to discuss this. Sometimes what you will see here is predictions rather than rules, and you will not know what really governs this, or you will not understand. I mean, you will know because you'll have the model, you can feed it input and see what happens. But yes, so the use of the word rules here is perhaps wishful thinking. Quite often we have predictions, but we don't really know exactly why and how they're computed.
Okay,
That
thank
answers your question?
Yes, it does. Thank you.
Okay, so let's see if we have, how would you sort with machine learning with no data? Okay. You will need data. And then one question is going to be, if you really want to sort, you want to learn a sorting program with machine learning, how would you do it? You will have to generate some data. Let's not discuss this now, but it's something that we can discuss a little bit later. So let's move on to defining supervised learning. So we consider systems here that apply a function f to input x and return an output y. We have an input space, which we're going to denote capital X, and elements in it are going to be lowercase x's. We're going to have y's that are output. Capital Y is the space, and element are going to be y's in it. And we're looking for a system that maps x's to y. The function that maps it is this function f. So think about the name then what as an element in the input, and the output is going to be a plus minus as before, plus or minus. So in supervised machine learning, we deal with systems where f of x is learned from examples. And as I said, we typically want to use it when the function f is unknown and we cannot just think about it. So in this sense, maybe the badges example isn't ideal because it's too easy. The paper, scissors, rock, paper, scissors might be a better example, or the spelling might be a better example because we actually don't know simple functions that can be used there. But in many, many examples, the function could be simple, nevertheless, we don't know it. So think about the spam function, or think about this question that I ask you, is Christopher Robin and Mr. Robin the same person or not? You don't know how to write a function that determines that. But hopefully, if you read enough and you've seen enough examples, you'll figure it out. and you will have your own internal function, and maybe you can train a model to do this. So that's the game we're going to play here. So we're going to have input, and item X is going to be a member of the instance space, and item Y is going to be a label space. There is some target function, we assume, that governs for every X that correct label Y. And we are after it. So we are going to learn a model that is going to be G of X. It may not be identical to F. We don't know what F is, but hopefully it's a good enough approximation of F so that we can live with it. So the space of all functions that our algorithm is going to consider, all the G's that are possible, is going to be the hypothesis space. So what we have here is the key three concepts that you want to understand for today: the instance space, the label space, and the hypothesis space. And we have a learning algorithm that is going to take this label training data, pairs of X and Y. X is the name, for example, Y is the plus or minus, the label, and it's going to output a model, a function G of X. Now, G of X is the model that we're going to use later on in your application. Now, think about it. So we started with an input example, then what was a plus, but really what the algorithm is going to see is not going to see then what. It's going to see some encoding of then what. For example, if I take the character-based representation, I'm going to split the name into characters. I'm going to encode each character as what we call a set of features. And now the name then what becomes a vector in this Boolean space, zeros and ones. And this is an element in the instance space. So the instance space is the space of all inputs the algorithm sees, and it's not necessarily the same. Typically, it's not the same as the one that you see here. Okay. Hopefully you can see my mouse. It's not the same as here. This is the instance space is already an encoding of this name. And similarly, so it's basically, this is a single element. This vector is a single element of the instance space, and there could be many, many such vectors that we will see. The learn model G of X could be a set of rules like this. If the ith character of the jth token is something, and the kth character is something, then say negative, otherwise say positive. So this could be an example of a G of X, a model that you learned. Another example could be this neural network that we learn. Again, it takes the character-based representation in this case, does something, and computes a function that predicts whether this specific example is positive or negative. So again, there could be many, many models, and that could be many decisions that you as the algorithm designer will have to make. You'll have to make decisions on how are you going to represent this input on the left, and you're going to make decisions on how you're going to represent the what functions you're going to allow your model to learn. Whether there are going to be these symbolic functions that are very easy to understand, or perhaps these networks that are a little bit more difficult to understand. Okay, so what is the protocol that we're going to do? So after we're learning, first of all, we want to test, right? So we want to know how well are we doing. So we typically reserve some label data for testing. So this is our test data. We know what the labels are, but we're not going to show this to the algorithm. So we're going to take the raw text data, only the X's. We're going to run the algorithm and test whether it agrees with the Y's that we held. So this is our learn model. We're going to predict the label G of X and compare them to the Y's. How do we compare? It really depends on the question. Sometimes we compare by just testing whether they are equal. Sometimes we compare by testing whether they are close enough. It really depends on the application, and we're going to see many examples of this. So now that we have these basic concepts, what are the key issues that we want to address? And this is really one of the important slides that is going to stay with us for the next couple of weeks. One question is modeling. How do we formulate application problems as machine learning problems? And part of it is how do we represent the data, and what is the learning protocol that we're going to use? A second question is the representation. And this has really two components. One of them is what functions do we want to learn? Do we want to learn a set of rules? Do we want to learn some continuous functions? And the second part is how do we map the input, the names, say, to an instance space? And of course, there's a question of, is there any theory for this? Any rigorous way to find this or general approach? Really, the answer here is going to be no, but this is a key question in machine learning. And finally, algorithms. What algorithms do we want to use? What are good algorithms? How do we define success? How do we know whether we are just overfitting our data or we are actually going to generalize well to future previously unseen examples? And of course, there's a computational problem. When you run an algorithm, you want to know, is it efficient enough? What are the computational issues here? So these are the issues that we're going to talk about, and I'm just going to say exactly the same thing in different words. So one question is, what is our instance space? Which means, what kind of features do we want to use? What is our label space? What kind of learning task are we dealing with? Is it going to be a Boolean classification, plus or minus? Is it going to be categorical, like choose a folder from among the 200 folders that I have? Is it going to be a ranking problem? What is our hypothesis space? So what is the space of functions that our algorithm is going to consider? And what learning algorithm are we going to use to choose the function? And how do we decide whether we are doing well or not? How do we measure success? And what drives learning? This is going to be the notion of a loss function that we're going to introduce. So, questions so far?
Can you go back to the last slide for a moment?
This one?
Yeah, sorry, I just couldn't get it all down.
Yes, so by the way, all of it, I mean, it's good that you're trying to get it all down. Everything is going to be in about an hour online. And the recording is also going to be online. That will take a little bit more time. Okay, so questions? No questions. I don't know why this is so slow, but gives you some time to breathe.
I asked the question, it's just not shown up yet.
Go ahead.
So is there a rule of thumb for how much data should be reserved for testing versus training in a data set?
There is a rule of thumb, 20%. But we're going to discuss this a little bit and see if that's the only way to do it, to just split. Even when we split, we can do it in multiple ways. I didn't want to get into it, but even in the multi-layer perceptron, the neural network that I showed some examples of before, the way I split the data is going to change the results. Even if I choose the 20%, here are examples of two ways I could do it. One way is I could just take the data that was given, 270 for example, or something like that, and sample 20%, put it aside for test, and the rest 80% I'm going to train with. That's way one. Another way is to split it first to positive and negative and sample 80% of the positive, sample 80% of the negative, I mean, and make sure that I have a data set that has the same distribution, balanced distribution as all of the data. So this is going to give me different results. And it's not the only way to do this. So the rule of thumb is 20%, but we're going to discuss this a lot because typically we want to do more than just train and test. We also want to have some development set that allows us to tune some parameters in case our algorithms have parameters. Okay, could you explain hypothesis space again? So, okay, so let me first go here. Okay, so here is where I introduce the notion of hypothesis space. So there is some target function that is hidden from us. In the badges game, this was the second character of the function of the first word is a vowel. And then I have a set of functions that my learning algorithm will consider. There could be many, many functions there. Maybe the functions there are functions of characters, but they do not have the notion of a vowel. They just know whether the character is A or B or C or D and so on. Then I'm going to learn some function. I don't know which function it's going to be yet, but I'm going to learn some function of characters. It's going to be different than the target function. But it could be a very good function. Could perform exactly the same, definitely on the training, but maybe there was never a letter, the letter E was never, in my training data, was never a second letter of any of the first words, and then my G will not know about E. So the space of all functions is the space of hypothesis spaces. Now I need to choose which one to use. For example, on the right here, I have two functions. The first one, the top one, is a neural network. It takes characters as input, as I suggested, and it does some computation over it. So there's a very, very large space of functions that this architecture can compute. We're going to get to discuss this in many details, but you can imagine that each one of these wires that you see there has a weight on it, and it multiplies the input by this weight, and then it sums it, and then the computation goes down this architecture. So there are many functions, depending on the weights that you put on these wires, that my learning algorithm consider. All these functions are my hypothesis space in this case. In the second example at the bottom here, it's a very, very different set of functions that my algorithm consider. It considers symbolic functions over characters, and it has conditions. If the ith character of the kth token has this value, then do something. And maybe conjoin this with multiple rules. And if something else happens, then say it negative. So again, there's a range of functions of this type. And my algorithm, I consider this. So the collection of all functions my algorithm consider is going to be called my hypothesis space. Okay, so let's move on. I want to talk a little bit about instance space and probably be done with it for today. So the instance space is really, really important because, as we show already, if I don't choose right, there's no chance I can get it. If I don't know in the badges cases that it depends on characters, and I think that it depends on the whole words, it's not going to do it. So let's think about this example. So in this case, I have an email message And my goal is to file it into one of 200 different folders that I have. In this case, the folder is sys519 fall 18. What kind of instance spaces would you consider here? Right, so I'm going to ask you to suggest an instance space for this email classification problem. And let's consider one of three types of instance spaces, either a Boolean set of features or a set of numerical features or other, choose your own. So in your response, please choose which one of them and then give two examples. So if you choose one, give me example of two Boolean features. If you choose two, give me examples of two features. But 519 is not a feature. I'm looking at the first example here because what does it mean? A feature has to have some semantics. You can say numerical, how many times the string 519 appears in my input. That's going to be a numerical feature. A Boolean feature is going to be, do you see the string 519 in my input? Yes or no? So let's get some more answers here. So choose the space that you care about. Do you want to use it? Do you want to use a Boolean set of features? Do you want to use a numerical set of features or some other ideas? And choose some features. Now remember, a feature really is a condition on the input. And it asks, what is the value of this condition if you are looking at numerical features? Or it asks whether it's present or not. Very slow, even though I see that a lot of you responded already. Okay, so 3, you suggest to look at the domain of the sender. That's excellent. That's another type of feature. 3 could be keywords, right? So I can just represent the email message as a set of words or a bag of words, we're going to call it. Boolean, spam or not spam. So that assumes that I have some classifier that knows whether something is a spam or not. Let's assume it's true, then it's a Boolean feature. Sent from a feature from a person in my contact list or not, that's a Boolean feature. 2 could be number of capital letters in the email. Excellent. So all these are features that you may want to use when you extract this. So let me just summarize this. All these are really good features. Whether 519 appears, number of words, length of words could be numerical features. So here are some of my examples. If I want to use Boolean features, is there a folder name after the sender? Does the email contain the word class? Does the email contain the word waiting? Does the email contain the word class and the word waiting? Actually, this is something I want you to think about. The fourth feature here, does it add anything? Or is it the same? Because I already asked, does it contain the word class and the word waiting? Think about it. I'm not going to answer it now, but we're going to think about it a little bit later. Numerical features. How often does the word learning occur? How long is the email? How many emails have I seen from this sender over the last day, week, month? And you can also think about type 3, just list all the tokens in the input and think about it this way. So, okay, so here are some examples for the badges game. And I'm going to stop here. I was hoping to get a little bit further, but I'm still going to ask you these two questions. Hopefully, it will take just a second for you to respond. this is a question that you've seen before. Okay, so you didn't like it. Hopefully you will also send me email or Piazza message explaining why. And also I want to ask these questions. Okay, so thank you very much. Again, please send email or send Piazza queries or feedback. And otherwise, I'm going to see you on Monday. Have a good weekend.